All right, let's check out some theorems, okay? So like I said, individually when we use these, they're pretty straightforward, pretty simple. When we mix them all together, that's when it starts to get more challenging. So make sure you're continuing to push yourself to practice these, to try to remember the rules, so on and so forth, okay? Because today we're going to put together, or actually we're not throwing in inscribed angles, that's next class. But today we're going to look at different chords. So we've looked at minor arcs and major arcs, okay? Today we're going to kind of put those to use with looking at different chords inside the circles. So several different theorems here today. So we have the congruent corresponding chords theorem, okay? So essentially what that tells us on that first picture there is if we have two congruent chords, their corresponding minor arcs are congruent, okay? So if we have two congruent chords, the minor arcs outside of those are congruent, as you can see by the picture. Pretty straightforward there, correct? Any questions? Okay, then it gives us an exercise. It says if measure of AB equals 110, find the measure of BC. You can see that that chords AB and BC are congruent, so their corresponding arc lengths AB and BC should be congruent as well, so that'd be 110. If AC was 150, find AB. I'll give you about 10 seconds to figure that one out. Okay, what kind of math am I looking at here? What should I do here? AC is not one of my congruent arc lengths, right? So what could I do? Yeah, Joe?
You could figure out how much you need to make a full circle and then divide it in half.
Okay, yeah, I get what you're saying. Okay, so we know the full circle's 360, right? Once we take off AC, so take off 150, then we'd be left with what, 210? No. Yeah, 210. Okay, then if we had 210 for the rest of it, we know those two remaining arc lengths should be congruent. So 210 divided by 2 would leave us with 105, right? So we can kind of work through it that way. All right, let's look at a couple more theorems here. Okay, so we have the perpendicular chord bisector theorem. That tells me if I have a diameter, and if that diameter is perpendicular to a chord, then it must be the bisector of that chord. Okay? So if a chord is a diameter, so meaning if it goes through the center and it's perpendicular to another chord, it must also bisect that chord. We also know that if two chords are perpendicular bisectors of each other, or not of each other, sorry. If one chord is a perpendicular bisector to another chord, it must be the diameter. So even if we don't see the center of the circle, so if you look at that third picture down with STQRP, okay, you can see that SQ is a perpendicular bisector of TR, right? You can see that? So you must be able to assume that SQ is the diameter and therefore must go through the center of the circle. We don't necessarily know where the center of the circle is, but we know that SQ must be the diameter of that circle. You guys understand that? Mm-hmm. Can I get a 3, 2, 1, 0 where you're at? Just on understanding what I just said. Okay, we're feeling good. Okay. All right. Go ahead and do exercises 3 and 4. Okay, so first we're looking for CE. We see that BD goes through the center of the circle, meaning it's the diameter. That means it should be a bisector of CE since it is perpendicular to CE. So if it is a bisector of CE, that means FE must also be 5. So CE must be 10. Okay. The measure of angle CE. We know that 9x should be congruent or equal to 80 minus x, right? Because it not only bisects the chord, but it also bisects the arc. So we can figure out that 9x equals 80 minus x. Add x to both sides, we get 10x equals 80. Divide by 10, x equals 8. So that means each of these has to be, what, 72? Okay. So that would make 144. So that means the measure of angle CE would be 144. Okay, any questions so far? A couple of pretty basic rules there. Okay. And then we have one more theorem, the equidistant chord theorem. It states that if two chords are equidistant from the center, they must be congruent. So two chords equidistant from the center, they must be congruent. Same is true that if two chords are congruent, then they must be equidistant from the center. Okay? So there's a couple different things that we can do with that as well. Okay? All right, let's go to the back page. You guys know that's where all the fun happens. Go ahead and do those 8 together with your groups, and then I'll come around, and then we'll go over them and everything. Okay? So I'll give you guys some time to do those 8 together with your groups. Go ahead. Okay, so you can see my answers to the first 4 up on the board. The measure of WX should match the angle measure of WQX, which WQX is a vertical angle to ZQY, which is 42 degrees. So I transfer that over with vertical angles, and then I know the measure of the central angle is the same as the measure of the arc length. Okay. Then I hit W. Oh my gosh, I can't read. I'm looking at the wrong one. That's why. YZ. Okay. YZ corresponds with or is congruent to WX. So we get 3.6 there. And then measure of angle X. Oh, I'm skipping over. Oh my gosh, I'm struggling today. WZ corresponds with XY, which is 9.2. And then the measure of XY. So if I'm trying to find this measure here, I'm going to have to find its central angle. Okay? So its central angle there looks like it is supplementary with 42, making it 138 degrees. So the arc length then is 138 degrees. Any questions on those first 4? Okay, let's keep trucking. 5 and 6 were pretty straightforward. I see that I have a diameter that is so on number 5 I see I have a diameter that's perpendicular. That means it should be a bisector. So I set those two expressions equal to each other, and I get x equals 3.6. And then same thing on number 6. Those two segments or two chords, no, not chords. Those two segments should be equal to each other. So I set them together and get x equals 6. Any questions there? Okay. Notice the directions are a little bit different on 7 and 8. What do the directions ask you on 7 and 8?
Find the radius.
Find the radius. How many people stopped here? I'm guessing a lot of you. Probably because you got stuck in the rhythm of finding x on 6 or on 5 and 6. That you just kept finding x on 7 and 8. How many people tried to find the radius? Anybody successful? Anybody want to tell us kind of the process you went through to find it? Because remember, we're not finding the chord, the length of the chord. We're finding the length of the radius. Yeah, Joe?
What I did was I used the PE. It says that if that is, I assumed that since it was a perpendicular bisector to DF, that was the diameter line, which would make that the radius. That's what I went through.
Right, but okay, so here's my only question. Does PE go all the way to the edge of the circle?
No.
No. Yep.
So DF is, since it's a perpendicular bisector, it's supposed to be the diameter, right?
DF?
Yeah.
No. It is not a perpendicular bisector because it does not bisect PE. So remember, the one that does the bisecting is the diameter. So Joe is kind of onto it. Well, kind of, sort of. Joe said PE should be part of the diameter. which is true. That would be part of the diameter if that chord went all the way across, or if that radius went all the way to the edge of the circle. How about I draw my own line? Can I draw my own line?
Sure.
Sure. You guys out of ideas, or anybody have another idea? Anthony, you have an idea?
Use Pythagorean theory to make a triangle from P to C.
From P to C. Perfect. Okay. So I draw my own line in, just like they're saying. We go from P to C. And to be totally honest, you could go from P to D, P to A, P to F. It doesn't really matter. What I know is this side is 3. My X value that I just got was 2. So I know if I plug 2 in right here, that 5 times 2 is 10. 10 minus 2 is 8. This whole thing is 8, so this thing must be 4, right? Because the diameter is a perpendicular bisector, so since it bisects that, it cuts it in half. So it looks like I have a bottom leg of 3, a side leg of 4, and I can go ahead and find the hypotenuse, which the hypotenuse will end up being the radius, okay? So I have 3 squared plus 4 squared equals radius squared. You guys know this special right triangle? Remember we talked about Pythagorean triples? This is a special Pythagorean triple. What? You guys ever heard of the 3, 4, 5 right triangle?
Yeah.
Maybe, sort of. I mean, you can always do Pythagorean theorem if you want to. I just didn't know if you guys knew that. So 9 plus 16 equals r squared. That means 25 equals r squared. Take the square root of both sides and you get r equals 5. Okay, now I'll go ahead and give you guys a minute to finish 8. So if you haven't finished 8, we kind of gave you a little framework there. This one's slightly different than 7, so take your time and do it right, but I'll give you a minute to go ahead and do 8. Okay, so since I know x is 3, I'm going to draw in my third side, my hypotenuse, if you will. Okay, I know that this side, YV, has to be half of that chord, so that's going to be 10, a really ugly 10. There we go. I can plug x in to find the bottom leg, so 4 times 3 is 12. 12 minus 5 is 7, so this bottom leg is 7. And then I have 10 squared plus 7 squared equals r squared. So I have 149, whoops, what's happening? 149 equals r squared. Take the square root of both sides. Somebody want to help me out? What's the square root of 149? 12.2. So my radius is 12.2. Okay, can I get a comfort level? 3210, how you feeling? Good. Practice makes perfect. Rest of the time is yours.